Hello everyone, welcome back to another kinetic tutoring episode. Today we're taking a look at 1.6 photoelectron spectroscopy. Let's just get into the first question. Here we're given the photoelectron spectroscopy of an unknown element, and we have to label each one of the peaks by its orbital and also find the identity of the element. So firstly, the first thing we want to do is to find the identity, and the way I like to do this is by counting the number of electrons. So here we have 1, 2, and 3, 4, 5, 6, 7, 8, 9, 10, 11. And all in all, we have 11 electrons. So if we take a look, that's going to be sodium Na. So that's our element Na, because sodium has the atomic number 11, and if we're talking in terms of atoms and not ions, if an atom's uh, no, number of protons is 11, that means the number of electrons is 11 as well in order to balance out the charges. So now let's write out the electron like the orbitals for sodium. So we have 1s2, 2s2, we have 2p6, and 3s1. This is going to be the electrons in their respective orbitals for sodium. As you can see, there's 2, 4, 10, 11. And so if we want to label the peaks, the first one is the one in the first ring is going to have the strongest charge. So that's going to be this one right here. This is going to be 1s2, because the electrons that are closest to the protons feel the strongest pull. Because if you remember from last lesson 1.5, the charge or the attraction of a positive force and a negative force is oppositely proportional to how far away they are, meaning if they're further away, the force grows weaker, and if they're closer together, the force grows stronger. So then the second one is going to be the second closest. This is going to be the 2s orbital. I didn't need to write this 2 because that's given by the fact that this peak is 2 electrons tall. Here we have 2p, and here we have 3s. All right, let's move on to the next question. A partial photoelectron spectroscopy of pure phosphorus is shown on the spectrum above. Draw the missing peak that corresponds to the electrons in the 3p sublevel. All right, so first let's write out what the electron list for phosphorus looks like. We have 1s2, 2s2, 2p6, 3s2, 3p3. And we're missing the 3p sublevel, so we have 1s here, we have 2s, and then we have we have 2p, and then, hold on guys. Sorry, I confused myself for a second. But we have 1s, 2s, 2p, 3s, and now we need to draw the 3p. So as we can see, the 2p is just slightly to the right of 2s. So the same thing's going to apply. 3p is going to be slightly to the right of 3s, and it's going to be 3 electrons tall, because as we can see here, the amount of electrons in the 3p orbital for phosphorus is going to be 3. So now let's move on to the final question. The table above shows the binding energy for the 1s electrons in a nitrogen atom and the binding energy for the 1s electrons on the oxygen atom. Explain the difference in these two values in terms of Coulomb's law. Alright, so we know that the 1s electrons in nitrogen and oxygen, they're the same, meaning that there's the same amount because they both have a full 1s orbital. So what makes it different is the amount of protons, because Coulomb's law states that the stronger the positive charge and the negative charge are, um, the the stronger the binding energy is going to be. So the reason the binding energy for oxygen is greater than the one for nitrogen is because there's more protons in the oxygen nucleus, meaning that the 1s electrons are going to be closer together, or closer to the protons, because they're getting pulled in more by the 12, or sorry, rather by the 8 protons compared to nitrogen 7 protons. So that's all I have for you guys today. That's all you need to know for 1.6. If there's any comments, questions, or concerns, make sure to leave them in the comment section below. And if you enjoyed this video, or if you learned something new, make sure to leave a like and subscribe, and I'll see you guys next time.